Today we want to continue looking at linear transformations. Remember, a linear transformation is a map that goes from one vector space to another vector space. For now, we're going to use Rn and Rm as our domain and codomain. And all we're doing is mapping every vector in the domain to a vector in the codomain. A linear transformation is a transformation that respects vector addition and scalar multiplication. That means if we have a linear combination in the domain, the image of a linear combination in the domain is that same linear combination of the images in the codomain. And so t of x plus y is equal to t of x plus t of y. T of 5 times x is 5 times t of x. That's the linear transformation respecting scalar multiplication and vector addition. We saw this with rules for differentiation. The derivative of a sum of functions is a sum of the derivative of the functions. That's a linear transformation. So here's the claim that we're making today. If we have a linear transformation, then there is from Rn to Rm, there's an m by n matrix A that implements the map. That is, t of x is equal to a times x for all x in Rn. So let's take a look at an example. Here we have the image of x1, x2. x1, x2, this is our vector x that we're starting with. We're starting with a vector in R2. So here's our vector from R2. That's what we're starting with. And notice that what we have on the other side is a vector in R3, and each component is a function of x1 and x2. We combine the x1s and x2s in a particular way. So here's the image t of x. Here I've written it sideways in the space-saving way, but we're saying that the image of x is going to be x1 minus 2x2 minus 2x1 minus x2 and 3x1 plus 2x2. So we can see that t of x, the image of x, is in R3. So we start with a vector in R2, and we put the coordinates together to come up with this vector in R3. So I wanted to put different colors, although it's a little hard to see. So I'm going to emphasize the commas. I think if you use a bold comma, you have to put extra dramatic pause, also known as a Shatner pause. x1 minus 2x2 minus 2x1 minus x2. I don't do a good Shatner, but there are certain impressions that don't have to be good. You just have to have the certain aspects of it, and people will get what you're talking about. I don't have a good Schwarzenegger, but if we start saying, yeah, we have to have matrix A that implements the map, you know what I'm going for? And so it doesn't have to be good. So, you know what I mean? So here's the way we want to think about this. We're not doing this because we have to do this, because there's a shorter way, there's an easy way to find what the matrix of the transformation is. You could probably guess what it's going to be, but we need to have an idea about how to find a linear transformation. So to find the standard matrix of a linear transformation, actually I got to say it this way. The columns of the standard matrix of a linear transformation, that's what I'm talking about. The columns of the standard matrix of a linear transformation are the images of the standard basis vectors. And a new term has appeared. The columns of the standard matrix of a linear transformation are the images of the standard basis vectors. What this means is that to find the matrix of a transformation, we map the basis vectors. That's what we get out of this. So, oh, that's fine. To find the matrix of a transformation, we map the basis vectors. Notice that in this little description where I say to find the matrix of a transformation, we map the basis vectors. I left off the word standard. The standard basis is a particular basis that we use to describe Rn. But there are others. They're like skywalkers. Apparently they're all over the place. And apparently, no, I don't want to say that. I don't want to spoil anything. It's too soon. You can say things like Darth Vader is Luke's father. That's not a spoiler because that movie came out in like 1981. So if you didn't know that by now, you don't get to have that. There's a statute of limitations on spoilers. Darth Vader is Luke's father. It's been long enough. If you haven't seen it by now, you don't get to have that one. And then we can kind of judge the quality of the reveal by if we still see it and it still gets us, then we're like, oh yeah, that was okay. It was okay to know that. You know, like fly, you fools. That still gets me. I know it's going to happen. I knew it was going to happen then, but still gets you. So when I talk about the standard basis, we need to talk about the standard basis for a vector space. So the standard basis for R2 is 1, 0 and 0, 1. I haven't even defined what a basis is. But that's okay. So the standard basis for R2 is 1, 0 and 0, 1. Here's why we like this as a standard basis. It is really easy to write any vector in R2 as a unique linear combination of these two vectors. This is why this is the standard basis. So the reason that this is going to be our standard basis is that it's super easy to write any vector in R2 as a unique linear combination of these vectors. That's what a basis is. It's the building blocks for the space. That means everything in the space can be described as a unique linear combination of your basis. So the vector 5, negative 3 is 5 times this first one, 1, 0, minus 3 times this other one, 0, 1. This is what we're talking about when we have a basis. A basis for a vector space is a linearly independent set of vectors that spans the space. This is why we care about basis. We can describe everything as a unique linear combination of those vectors in the basis. So this is why when we want to find the matrix of a transformation, all we need to do is map the basis vector of a linear transformation. All we need to do is map the basis vectors. Because if we can write everything in R2 as a unique linear combination of the vectors 1, 0, and 0, 1, and since the transformation is linear, it will respect that linear combination. We just have to look at what the images of these basis vectors are. And then we'll have the matrix of the transformation. So let's do that. I don't know if I left my space. I planned to put it in this corner here, but I wrote this a little bigger than I planned. So, I mean, if you had like an actual professional teacher, they would have planned this out better. And there would have been like a PowerPoint and things would have like just appeared. And it wouldn't just be a camera pointed at some dude writing. But I was going to say writing on paper, but this is an actual paper. But you're stuck with me, so there you go. So let's map the basis vectors for this example. So t of 1, I want to find t of 1, 0 and t of 0, 1. See if I can fit all of it. Barely. So t of 1, 0. So x1 is 1, x2 is 0, and I just need to find the image by plugging into these three expressions. So t of 1, 0 is going to be 1 minus 2 times 0, so it's just going to be 1. T of 1, 0 is going to be 1, and then negative 2. And 3x1 plus 2x2 is 3. Now, this is the image of the first basis vector, and so this will be the first column of the matrix of the transformation.
Could you explain how did you get 1, negative 2, and 3 again?
I just took x1 equals 1 and x2 equals 0. So x1 is 1 and x2 is 0. And so the 1 is this expression x1 minus 2x2. So when I look at x1 minus 2x2, I have x1 is 1 minus 2 times x2, which is 0. So we get the 1. So then we do the same thing for the negative 2. I have the second coordinate is negative 2x1 minus x2. So I have negative 2 times x1 minus x2. And so we get negative 2. And the same thing for 3. So there's the first column. It shows up as a row because of the way we chose to write down our transformation. That's the first column of the standard matrix. Now we need to find the image of 0, 1. Now x1 is 0 and x2 is 1, so we're going to get negative 2, negative 1, and 2. There's the second column. I just plug x1 and x2 into my transformation, and here's our second column. So the standard matrix of T is 1, negative 2, 3, negative 2, negative 1, 2. Oops. Let's do an example where we run a vector through the transformation just using the initial definition, and then multiply that vector by this matrix and see that they come out the same. All right. Unfortunately, I ran out of space on this page. So T of x1, x2. So the claim that T of x1, x2 is equal to x1 minus 2x2 minus 2x1 minus x2 and 3x1 minus 2x plus 2x2. And we're also saying that T of x is equal to ax, where A is this 3 by 2 matrix. It's going to be 1, negative 2, 3, and negative 2, negative 1, 2. And what you should observe right now is you say, hey, isn't that first column just the x1 column and the second column is just the x2 column? And yeah, that's absolutely the case. This is why we love the standard basis so much. Look how borderline trivial it is to come up with this matrix. Why are we doing this map the basis vectors business? And the reason is we're not always using the standard basis. So we need a generalized thing. We can't just always say, well, we'll always be in the standard basis, because the standard basis might not be convenient for our purposes at the time. All right, so let's experiment. Let's find T of 5, negative 3. So I'm going to have 5 minus 2 times negative 3, and then negative 2 times 5 minus a negative 3, and then 3 times 5 plus 2 times negative 3. See what we get here. It's arithmetic, and so I'm going to mess this up because it's I'm not very good at arithmetic. So it's going to be 5 plus 6, or 11. And it's going to be negative 10 plus 3, which is negative 7. And 15 minus 6, which is something, 9. I should be more confident about that, but 9. Now let's multiply the vector 5, negative 3 by the matrix A. So if I take the matrix A, and with its 1, negative 2, 3, and negative 2, negative 1, 2, and multiply it by 5, negative 3, I'm going to make a linear combination of the columns of the matrix A using the entries in X as weights. So I'm going to have 5 times 1, negative 2, 3, minus 3 times negative 2, negative 1, 2. And we can see that we're doing the same calculations. So it's going to be 5 times 1 minus 3 times negative 2. And there's going to be a 5 times a negative 2 minus 3 times negative 1. And there's a 5 times 3 minus 3 times 2. It's the same 3 calculations we did above. And so we get the same vector, 11, negative 7, 9. The reason that this works is that T is a linear transformation. And so we mapped the basis vectors, and the combination that we use to build 5, negative 3 out of the standard basis vectors is the same combination we use on the images of the standard basis vectors. The matrix is there because the transformation is linear, and the transformation respects this linear combination. This 5, negative 3 is 5 times the first vector minus 3 times the second vector in the standard basis for R2. And we have the same linear combination here after when we implement the map. 5 times the image of 1, 0 minus 3 times the image of 0, 1. Since t is linear, t respects this linear combination. So earlier, I had written t in a vertical format, and you can just separate out the x1 and x2. The trick is remembering that the images of the basis vectors are going to be the columns of the standard matrix of the transformation. But notice that if I write t vertically, then it's really easy to kind of separate this out. If I write a vertical image, x1 minus 2x2, minus 2x1 minus x2, 3x1 plus 2x2. If we're using the standard basis, then we can just kind of break this apart into an x1 vector. Oops. I was here to pull out the x1s and I didn't even do the thing that I intended to do. So it's really easy to get this, here are the columns. It's really easy to get the columns of the matrix of the transformation when we're using the standard basis. It's easy to get the standard matrix of the transformation. But we're not always using the standard basis for R2 and R3. All right, let's pause the video here. And then we'll come back and talk some more about linear transformations.